Imagine a waterfall. Imagine the water in the river flowing downriver, and as it gets to the waterfall, maybe the river narrows, the water gets faster and faster, and at some point the water flows so fast that even sound cannot escape. A person in a rowboat passes a point of no return, cannot row faster than the flow of the water. And so once you pass a certain point where the velocity is too strong to overcome, you're doomed. You're going to go over the waterfall. The edge of the waterfall is like the horizon of the black hole.
I don't know whether it's you or just circumstances that have always attracted you to what I'll refer to as the cutting edge, whether it's in quantum gravity or black holes. But were black holes something that always gripped you even before the black hole war?
No. I was originally a particle physicist, and my interests were elementary particles, not gravity. In fact, when I was a very young physicist, it was considered by most particle physicists that gravity was a waste of time, that the quantum mechanics of gravity was very far away from any possible experiment, and there was probably no way for the next 500 years. I think Dick Feynman himself said he didn't want to work on the quantum mechanics of gravity because he thought it would take 500 years before we'd have any experimental evidence. That was the general opinion, and I don't know if I shared it. All of my elders had that view, and I more or less accepted it. I worked on particle physics, I worked on quarks, I worked on all those kind of things. Gravity only became really interesting to me around 1980. Now, that may seem like a long time ago to you, but it's not so long ago for me.
What happened in 1980?
Particle physics just ran out of steam. There were no new experiments. There was no good ideas about how to go past the standard model of particle physics. It had gotten stuck, badly stuck. It wasn't just me. It was a large number, mostly people younger than me, who just said, this is just not the way to go. Let's worry about gravity. And maybe gravity will not be as hard. Gravity means quantum mechanics of gravity. Maybe it's not as hard as all those people were saying. Nobody studied it very much. The other thing that made a big impact, I have to say, it made a big impact, although it didn't make an impact on me until around 1980, was Stephen Hawking's discovery that black holes evaporate. That as a consequence of quantum mechanics, black holes evaporate. And his claim that meant that information is lost inside a black hole and can never be regained, that struck me very deeply. I suspected that was wrong, didn't sound right. My friend at Hooft in Holland, who was a very famous physicist, also didn't believe it. We talked about it. And I think the thing that really precipitated my interest was a meeting that took place, I think it was around 1980 or 1981, in a mansion in San Francisco where Hooft, Hawking, and a good number of other people met. And Hawking made his claim that information is lost when black holes evaporate. Hooft was there, I was there, and we were both very, very puzzled. Sure, Stephen was wrong. And that was the kind of problem that I really can get my hands into, that I really like, when there's a kind of clash of principles. Quantum mechanics saying information can never be lost. Gravity, apparent, black holes apparently telling you that information is lost. That was a conflict of principle. Two different ways to think about nature were leading to radically different, and not just different, but opposing views of the relation between quantum mechanics and gravity. And, once you get hooked on a thing like that, if you have the particular mental makeup that I have, you're stuck. You're not gonna turn back.
One of the major themes of the black hole war is this really deep conflict between quantum mechanics on the one hand, you and it Hooft, and then general relativity, the relativists like Stephen Hawking on the other.
Yeah.
And I have had some conversations on the show about topics adjacent to this area. So I spoke with Juan Maldacena all about holography. But for our listeners who...
Now, keep in mind, Juan is, of course, a very great physicist, but he's a good deal younger. And so he wasn't present during this period when all of this conflict was taking place.
Yeah, all I wanted to say, though, was just for our listeners who haven't listened to those conversations, who aren't physicists, I think it would be really good to start out just by laying out the basics of black holes, of entropy, that are necessary to understand this war. So just what is a black hole that led relativists to believe that information would get sucked in and trapped there?
Okay. Black holes are objects which are so gravitationally powerful or intense. The matter within a black hole is so concentrated that a horizon forms around them. A horizon is, or I think one way to put it, is that it's a point of no return. Anything that falls past the horizon of a black hole is sucked in and can't get out, or at least that's the classical gravitational view of what a black hole is. Could you explain it? Here's a way we might explain it. Imagine a waterfall. Imagine the water in the river flowing downriver, and as it gets to the waterfall, maybe the river narrows, the water gets faster and faster, and at some point the water flows so fast that even sound cannot escape. A person in a rowboat passes a point of no return, cannot row faster than the flow of the water. And so once you pass a certain point where the velocity is too strong to overcome, you're doomed. You're going to go over the waterfall. The edge of the waterfall is like the horizon of the black hole, or the place, better yet, the place where you can no longer escape. That's the point of no return. That's the horizon of the black hole. Now, we're not in rowboats, and we're not worried about sound. What we're worried about is light. If the flow of the river could somehow exceed the speed of light, then light could never escape from some point of no return. That's exactly what a black hole is. It's a point where light, and if light, then nothing else, can escape the pull of gravity. That's the horizon, the point of no return. So black holes are fundamentally objects with horizons with a point of no return. That's what we can think of them as. What Stephen said is if there's a point of no return, then anything carrying some information, it could be, almost anything carries information, it could be a book. When it flows past the point of no return, it's lost. It's permanently lost to the outside world. And that's fine. So what? It's lost to the outside world, but it's in the black hole. But then Stephen also said, but black holes evaporate. So in the end of the day, something has fallen into the black hole, carried some information with it, carried some distinctions. There could be distinctions about what fell into the black hole. It might have been one of two books. It could either be Stephen Hawking's book or my book. The different. Okay? The distinction between what fell in will simply be annihilated because nothing can escape from the black hole, but on the other hand, the black hole evaporates. So there you have it. Information must be fundamentally lost. On the other hand, quantum mechanics is a theory where information is never lost. It can get scrambled, it can get put into a form which is highly inaccessible, but with enough effort, one should always be able to recover information of any kind. And one possibility is that the evaporation products of the black hole, the radiation which goes off, the Hawking radiation, actually carries that information. But Stephen said, no, that's not the way black holes work. Anything that falls in is lost. So there we had it, a conflict of principle. Gravity and black holes said information is lost. Quantum mechanics says it can never be lost. And that was the clash of principle that motivated me. Very few people were terribly interested in it. Hooft was the only other one that I know.
Which is surprising just because black holes are today, I mean, one of the hottest topics. But I recently
That's correct.
was in New York City and interviewed Jan 11 about black holes, and she really had a lot of nice things to say about your work and how inspiring
Jan
it
is
was.
an old friend.
Yeah, but
Don't believe nice things said by old friends.
But one thing that we discussed is whether or not the singularity at the center of a black hole is real. Because a number of physicists I've spoken with, like Jana or Eric Verlinde, they kind of view the black hole exclusively as the horizon.
Well,
and I just was wondering how you think about this.
Well, okay, this is also very puzzling. You may say that the black hole is only what is outside the horizon. If no information ever gets lost, just say everything is outside the horizon. But you also have to ask the question, what if you fell through the horizon of the black hole? What would happen? Most people who study gravity, and I'm certainly one of them, that would believe that very, very much like a waterfall. When the waterfall, you're flowing down the river in a rowboat, you pass the point of no return. What happens to you when you pass the point of no return? Nothing. You're just moving a little bit faster than you can row back. If you're just floating down the river, you feel nothing. Nothing special happens at that point. That's what's believed by most physicists, at least of my, most physicists like myself, that if you fell through the horizon of a black hole, you would feel nothing. You would just sail through just like the rowboat falling past the point of no return. So I don't think you can say that just forget about the inside of the black hole, just say the edge of the black hole is the horizon and there's nothing inside it. We're stuck with a puzzle. Yes, if you're outside the black hole and you always stay outside the black hole, every observation that you can ever make is consistent with the idea that there's nothing inside the black hole, just the horizon. On the other hand, if you're in a frame of reference falling in, you will pass the black hole horizon and you will have a perfectly good life, at least if the black hole is big enough, at least until you approach the singularity. Things get tough at the singularity.
Yeah,
that's a bad place. But the horizon, perfectly smooth. You know what it's like? Again, it's like the waterfall. When you pass the point of no return in the river, that's just where the velocity of the flow is a little bit faster than you can row yourself out of. Nothing special happens. Where does the really bad stuff happen? When you go over the waterfall and crash on the rocks below. The singularity is like the rocks below. The horizon is like the point of no return. And so I don't think it's possible just to say there's nothing inside the black hole horizon. An observer who falls through will see a perfectly ordinary space-time on the other side. But somebody on the outside will reckon that nothing ever went through the horizon. So it's a little bit crazy, very counterintuitive, and we've wrestled with that pretty much since, I would say, around 1980.
I mean, the question that immediately comes to mind is, are there two different realities then, or are just two different ways of looking at the same thing?
Yeah, I think it's two different ways of looking at the same thing. What happens from the outside when something falls, from the perspective from the outside, is when something falls toward the horizon, it gets all scrambled up and becomes highly inaccessible to the ordinary means of retrieving information. Information can get badly scrambled to the point where, I'll give you an example. Again, start with a book. And now we burn the book. Everything goes up in smoke. The information in the book is lost. No, not according to the really precise rules of quantum mechanics. The really precise rules of quantum mechanics say that that information is there in the smoke, but very hard to retrieve. It's gotten too scrambled, it's gotten too mixed up, it's gotten too inaccessible. You'd have to know every molecule of smoke. You'd have to know every single atom of smoke, exactly where it is, exactly where it's moving, how fast it's moving. If you knew all of that, and remember the number of molecules of smoke in a burned book is what, 10 to the 30th or some sort of ridiculously large number. If you had the capacity to process all of that information, you could recover whether the book was Stephen's book or my book. But it would be very, very hard, very, very complex. So in practice, you say the information is lost, but not in principle. With thought, the same thing is true of black holes. If you're on the outside of the black hole, what you see is all this Hawking radiation coming out, and that Hawking radiation is carrying the information of what fell in. On the other hand, if you fall through, everything is perfectly normal and the information passes to the inside. What we've kind of learned is that the inside and the outside are not two different things. They're really representations of the same thing.
Is this black hole complementarity?
That's black hole complementarity, that they're two different expressions of the same information. And they're not, I wouldn't say they were two different realities. I would say they were two different mathematical representations of the same thing. This happens in mathematics and physics sometimes, that different things can be expressed in different form. Transformations of one thing can look very, very peculiar from the other point of view. And that's pretty much what we think, that what falls into the interior, which you see when you fall through, is a kind of mathematical transformation of what's seen from the outside, but both carry the same information. Yeah, that's what's called black hole complementarity. That was a sort of last-ditch effort to try to make sense out of these two different views, but it turned out to be right. Or at least it turned out to be very consistent with what 80, 90, 2000, 2010, 2020, 40 years ago was a wild conjecture. It is now almost completely believed by the younger class of physicists who study these things.
Okay, just to push this thought experiment a little bit farther of kind of rowing the boat and there not being this huge difference beyond this point of no return in the velocity. I've just heard that a lot of crazy things happen once you pass the event horizon of a black hole, such as the space and time coordinates flipping. And
No. That's crazy things happen in the mathematics, in some of the mathematics. We've learned what all that means. There's nothing crazy about it. In certain coordinates, even ordinary, what we call flat space-time, that means space-time with no black holes, just ordinary empty space-time. In certain coordinates, the same thing can happen. A certain coordinate, which was introduced by the mathematician to describe space, it's not intrinsic to the space-time itself. A certain coordinate can, on one side of a certain line, be space-like, and on the other side, time-like. Nothing unusual about that. The media may play it up as a really wild thing, but there's nothing wild going on. Somebody falling through the horizon does not see space turn into time. He just sees space and he sees time.
Okay.
And if he looks out of the black hole, incidentally, he doesn't see anything very peculiar on the outside. Somebody on the inside, right, so that much is not a puzzle about space turning into time, time turning into space. That's a way that the media has of trying to make it sound very exotic.
Okay, yeah, I was just wondering if there are any sensational changes in the physics as you cross the event horizon, but it sounds like no, there aren't.
As perceived by the person falling through, no.
Okay.
If the black hole is small, then as you approach it, there are large, what are called tidal forces. But if the black hole is big enough, then the approach to the horizon is a non-event or an almost non-event.
I was on the phone with my grandfather yesterday, and he's 89, and he asked me if I had any interviews coming up, and I was telling him about this one, and he asked about it and black holes. And a question that he had, so I'm assuming that a lot of our listeners have, is he was puzzled by this concept of information, because it sounds to him more like computer science than physics.
Yes. Computer science is certainly, what's the right word? Infected its way into physics in a very, very strong. Infected is probably not the right word.
Invaded,
or it wasn't the computer scientists who pushed it into physics. It was the physicists who realized many of their needs for new concepts was already there in computer science. And one of them was this idea of information. But information simply means distinctions between things. You say that there's certain information that's stored in the distinction between my book and Stephen's book. Now, there are many, many pages in both books. They're different from each other. And so the number of bits of information, the number of distinctions that characterize the difference between his book and my book is large. Both books have more than 100,000 words. Each word has maybe 10 letters. Each letter is a thing on the printed page with lots of pixels. And pixels are made out of atoms. So all of those are distinctions, but there's a finite number of them, some very large number of distinctions that distinguish the two books. That's what information is. It's just distinctions between things. And that's what computer science is about, distinguishing different messages, for example. ... is different than ... Morse code is what I'm talking about. So when I send you a Morse code message saying I love my cat, and you might have thought that I said I hate my dog, you can look at the individual pieces of the Morse code and you can recover what I said. Even though the Morse code may just seem like a bunch of garbled nonsense to most people, if you know the code, you can recover the distinction between the two things. Okay, so what are we talking about? What distinctions are we talking about for a black hole? A black hole could be created, for example, by a star collapsing. All the material of the star fell in. But a black hole could also be constructed by just a large number of particles being focused in and sent in toward a point. Enough particles, ordinary elementary particles, electrons, protons, neutrons, positrons, antiparticles of all kinds, shoot them in, and when they come in, they will form a horizon, and you'll have two black holes which are formed in very, very different ways. Now, the classical black hole solutions, the solutions of general relativity, don't admit any distinction between these. They just are black holes. All black holes look the same. That's what drove Stephen to say information is lost. What information? The information about whether it was formed by a collapsing star or a bunch of elementary particles that came together. There's huge distinctions between the two, but they appear to be lost when the black hole forms. What we've discovered is that information is not lost. It's there in the outgoing Hawking radiation. So that seems to be what's going on.
And just to translate this idea of these fundamental pieces of information are called bits.
Bits.
And what are bits? How do you make bits rigorous as a physicist?
Well, that's a difficult question. Sometimes a physical system is set up in a language for which bits, not if it's a quantum mechanical system, they're called qubits, which means quantum bits, which are a little different than just the bits in your ordinary computer. But never mind that distinction for a minute. Certain physics problems are naturally amendable to being expressed in terms of bits. Other physical problems are not so natural to express them in terms of bits. So sometimes the use of the language of bits in computer science and so forth is a little bit unnatural for certain physics problems. For example, physics problems involving continuous fields. What bits are good for is when your description involves something very discrete, some very discrete variables. What it's not so good for is systems which are described by continuum mechanics. But in quantum mechanics, everything is discrete. That's the difference between classical and quantum mechanics. Everything is discrete. And so it's thought that if we worked hard enough, almost any kind of quantum system could be reduced to a system of qubits, quantum bits. That has not been done for most, for example, it's not really been done for the standard model of particle physics. But it's thought that because of quantum mechanics, everything does reduce to discrete information and could be represented in terms of qubits if only you worked hard enough to translate it into that language.
One slogan I wanted to ask about before we move on just a bit from information, maybe, is it from bit.
Oh.
What does that mean? Who said it?
John Wheeler. John Wheeler was a visionary. His great contribution to physics was, he did some good physics, but he was not one of the great technical physicists of his generation. His great contribution was a vision and the transferring of that vision to some very, very brilliant students, like Kip Thorne, for example, and people.
Have you worked with Kip Thorne?
No, I know Kip for years, but no. Okay, so what was the vision? The vision was that everything could be reduced down to bits. Every physical system could be represented in the language of bits. Even things which apparently seem to be described by continuous fields, because of quantum mechanics, everything could be reduced to bits. Now, he didn't use the word qubits, quantum bits. The word didn't exist at that time. He, of course, meant quantum bits. He could not possibly have thought that it was classical bits. So John Wheeler had this vision that physics could be reduced to, well, we could call it, physics could be reduced to computer science, quantum computer science, not classical computer science. That has turned out to be very much a current theme. It's not just a current theme, it's what almost every physicist that I know who's working on these things believes. So that was a vision. His influence on his students was monumental, not just on the students, but many, many other people. And so there was a greatness there, even though his own technical contribution to physics was quite modest.
Well, in keeping with this discussion of some big figures, I'd like to get back into the dialectic of the black hole war itself.
I never knew what dialectic meant.
Back and forth discussion.
Back and forth.
Yeah.
Okay, thank you. Now I know what a dialectic means.
Yeah. And first, I'd like to talk about one of the figures who is very important, especially at the beginning, and that's Jacob Bekenstein.
Yeah.
And
yeah.
So
we shouldn't have left him out.
Yeah. So why was his contention that black holes have entropy both so shocking and so integral to the development of the conflict?
Okay. So when does a system have entropy? What is entropy first? Entropy is hidden information, information that is really present in the system, distinctions between two systems, but sometimes that information is very difficult to perceive. Why? One reason is it might be behind some closed door somewhere where you can't see it. Okay, that's not so interesting. Another reason is because it might be contained among a set of degrees of freedom which is just so numerous and so tiny and so small that with our ordinary coarse-grained vision, with ordinary coarse-grained methods of observing the system, you can't see all this fine-grained information. For example, in a gas in a room, take this room, it's full of gas. You can't see the gas. Even if you could see one or two molecules in the gas, you couldn't possibly keep track of all of them.
Right.
But the presence of all of them and the details and everything else have a huge amount of information about what that gas is like, the details of it. So entropy is hidden information, either hidden because you just don't have access to it because it's in a locked box somewheres, or more importantly, because it's contained in so many degrees of freedom that are just so tiny and so microscopic that you can't keep track of them. That's what entropy is. Okay, so the question then is, do black holes contain information which is hidden? That's what's believed. It's believed that the horizon of the black hole, and later when the black hole evaporates, contains all the information that fell into the black hole, but it's hidden because it's so scrambled up among so many tiny degrees of freedom that we can't perceive it with ordinary methods. That's what it would mean for a black hole to have entropy. It would mean that the structure, the detail, the quantum details of the horizon can, in principle, tell you whether the black hole, whether it was Stephen's book or my book that fell into the black hole. That in principle, but it's so scrambled up and it's so in the form of tiny microscopic details on the horizon that for all practical purposes, it's inaccessible. That's what entropy is. Why did Jacob think that black holes have entropy? Well, there was a number of reasons, I think. I think he sort of intuited that information can't be lost. He intuited that, and he said, where can it be in the black hole? It must be in hidden details on the horizon. I think that's what he was thinking, that hidden details on the horizon must encode everything that fell in. And he did some calculations on that basis and found a rather consistent story about the missing information or the entropy of the black hole. For example, there was a known fact about black holes. Well, one of the things he said, through some calculations, which you can read about in my book, incidentally, that the amount of information in a black hole is proportional to the area of the horizon. It was known from classical general relativity that the area of a horizon always increases, never decreases. Well, that's kind of interesting, because the second law of thermodynamics says that entropy is always increasing, never decreases. I suspect that, I didn't know Bekenstein very well, and I never asked him about this, but I'm pretty sure he must have said to himself, this fact that entropy never decreases and the fact that horizon area never decreases must somehow be related. Somehow they must be the same fact. And so that encouraged him with the idea that black holes have entropy, and the entropy is proportional to the area of the horizon. It was a brilliant guess. It was a brilliant guess. What he didn't realize, this is the so-called first law of thermodynamics. If something has entropy and it has energy, then it has temperature. That's the first law of thermodynamics. dE equals TdS. Don't worry about what that means. That's the relationship between energy, entropy, and temperature. So he didn't realize that one of the things he was saying is that black holes have temperature. Now, Hawking recognized that, and at first what he said, we know that black holes don't have temperature. That's ridiculous. Bekenstein must be wrong. But then Hawking did his own calculation, completely from a different point of view, and found, yes, the black hole has temperature. And it was consistent with what Bekenstein had said about entropy. But then Stevens realized something else. He was very brilliant. He realized if a thing has temperature, it will radiate. It will radiate photons. And when it radiates photons, it loses a bit of energy. Mass, when it loses energy, it shrinks. It's radiating away entropy, and it's shrinking, and he discovered the fact that black holes evaporate. Okay, once he knew that, and the argument was completely compelling, black holes have entropy, they have temperature, they radiate like a black body, and therefore give off energy, and if they give off energy, they evaporate and shrink. Just like a puddle of water giving off molecules shrinks and disappears in the end. Well, then he said, wait a minute, what happened to all the information which fell into the black hole? Black hole's not there anymore. But it can't get out. So information must be fundamentally lost. He didn't take seriously the possibility that the radiation itself might be carrying off that information. That is basically where we disagreed. That the radiation carrying off the energy of the black hole is also carrying off the details of its formation, and eventually he gave up and said, yeah, you guys must be right. But, you know.
I'd like to come back to Hawking and the radiation in a minute, but first, I'd like to tie some things together and then maybe anticipate holography a bit. And what I'm wondering is, what is the connection between bits of information, Planck area units, and the horizon of the black hole?
Okay, well.
And maybe this is my Planck or Planck? What do you say?
It depends on whether you're German or...
okay.
If you're German, you say Planck. Most physicists will say Planck. I haven't heard Planck for a long time.
Okay.
Planck. The Planck unit of length is just a terribly tiny unit of length that can be constructed out of gravitational units and quantum mechanical units. H-bar, Planck's constant, when combined with Newton's constant of gravity and the speed of light, give a unit of length. It's called the Planck length. It's very, very, very small. about 19 orders of magnitude smaller than a proton.
Very small.
Very, very small. There's a unit of area which goes with a unit of length. You just square the unit of length and you get us a unit of area. That's about 10 to the minus 66 square centimeters, terribly tiny. Okay, now, what Bekenstein discovered was that the entropy of a black hole is proportional to the area of the black hole measured in these Planck units. So think of the horizon as being tiled with little tiny pixels, each pixel being about a Planck size. Count up how many pixels the horizon has. Just all you have to do is divide its area by the Planck area, and that will tell you how much entropy it has. So the three went together: area, entropy, and the Planck area.
And I'm sure that this is another question that is coming to mind for a lot of people is there's really nothing sort of special about the surface of a black hole beyond its being a point of no return? Well, then how can information be stored on it if it's not really a physical surface?
Okay. I didn't say it wasn't a physical surface. You
okay,
said it's
okay. I said it's not a physical surface.
I said for somebody falling in, nothing happens special. Somebody on the outside doing experiments. Let's imagine you're on the outside of the black hole. What's keeping you there? I don't know. Your rockets are keeping you there, or a string attached to somebody very, very far away. A rope is keeping you suspended above the black hole, or you're orbiting the black hole. One way or another, you're either orbiting or suspended above the black hole. And now you want to do experiments on it. How can you do experiments? You want to do experiments on the horizon. Well, here's a way. You could take a string. You have a fishing pole and a nylon fishing line, and at the end of the nylon fishing line, you put a thermometer. And you lower the fishing line down. Gravity is pulling the thermometer down toward the horizon. On the other hand, you can reel it back in. So you lower the thermometer down near the horizon. It records a temperature. Maybe it sends the temperature back to you, or maybe you just reel it in and see what the temperature was. You'll discover that it had the closer that thermometer got to the horizon, the hotter that temperature was. In fact, you'll discover that if the thermometer went very close to the horizon, the temperature can be very, very high. So it seems to be a reality, at least insofar as experiments done from the outside. It seems to be a reality that there's a hot surface there. On the other hand, if you allowed yourself to fall in, you would detect no hot surface at all. Not at all. So you would say, oh, there was no hot surface there. I think I'll tell my friend on the outside and therefore give him a contradiction. My friend who stayed on the outside claimed that he did all these experiments and found a hot horizon. But I fell through that horizon and there was no hot horizon. I'm going to tell him, and then he's in a real quandary. Okay. The problem is the guy who fell through the outside fell through the horizon, cannot communicate with the outside. He's past the horizon, past the point of no return, cannot send a message out. So it's all consistent, you see. Person on the outside says, horizon is a real membrane, it's a real thing, it's hot, it has properties, it has electrical conductivity, has all kinds of properties. So he sends his buddy in to pass through the horizon and send him out a message, telling him that whether there is or isn't anything there, but the whole experiment gets frustrated by the fact that his friend who goes into the black hole cannot communicate with the outside. So yeah, that's the dilemma, if you like. Nothing inconsistent. Nothing inconsistent turns up. But it is, I don't know whether to call it a dilemma or just a very counterintuitive property of black holes.
This is maybe getting a little bit ahead of myself here, but I'm curious why, if the information is not lost and everything that goes into the black hole does eventually come out, then wouldn't the person who passes over the horizon's experience of there being something or nothing in there eventually get back out and
Well, okay, I mean,
yield a contradiction?
in some sense or another. But I don't think he gets out any better than the person who jumped into a fire and comes out in the smoke and the ashes. If, better yet,
So it's incomprehensible.
completely incomprehensible and certainly not memory. And there's no memory of it in any ordinary human sense. But it's like, imagine you jumped into the sun and got not only evaporated but ionized, and a million years later, not a million years later, a couple of billion years later, the sun has completely given off all its energy, and you're now told that all of your bits of information will be in that radiation that goes out. It's very cold comfort. It's not going to mean that that radiation going out is you in any human sense. That radiation can't think. It can't do any of the things that you as a human being can do. But nevertheless, the details of who you were, what you were like, is encoded in that radiation. That much, incidentally, is not a conjecture. That much is built into our rules of physics. It's called unitarity in quantum physics. Doesn't matter what the word means. It means exactly that information can never be lost, and it'll always appear, although very badly scrambled and inaccessible. So same thing with a black hole.
Now moving on to another character. So Stephen Hawking, of course, is the figure opposing you in the black hole war. Was he a friend of yours? What was he like as a person?
Stephen
and as
wonderful.
A physicist?
Oh, he was great. Well, he was certainly a great physicist. Now, you could ask a question, an interesting question. Would Stephen Hawking be nearly as famous as a physicist if he wasn't Stephen Hawking? By Stephen Hawking, I mean a man navigating the universe in his magical wheelchair.
Okay.
No, he would be considered an important 20th century physicist, a very productive and more than productive, a great 20th century physicist. But he would be an ordinary great physicist.
Not an Einstein or...
Probably not an Einstein. I don't think an Einstein, no. But still, seriously great.
Can I distract you for a moment and just ask who you think are the other Einsteins of the 20th century?
I don't think there were any.
Okay.
I don't think there were any. I think he was, Newton, and an ancient Greek that you probably never heard of named Aristarchus were the three great geniuses of physics, I think.
Because I'm not sure I have heard of Aristarchus, maybe it's worth a minute or two just saying who he was or what he did.
Aristarchus was a Greek astronomer, physicist. I suppose you could call him a philosopher. I never liked the word philosopher very much. I never quite knew what it meant. He put together so much of what we subsequently knew and understood about the universe. I'm not talking about modern cosmology. I'm talking about Copernican cosmology. Copernican, that the Earth goes around the sun doesn't go around the Earth. He put that together, and for very modern reasons, incidentally. He understood that the motion of the planets was much better described by a sun at the center and planets going around it than the Earth at the center and everything going around it. He figured out how to measure the distance to the sun. His instruments were not sufficiently precise to make that measurement in detail, but he did figure out that the sun was at least 60 times further than the moon. It's much more like 400 times further, I think. He was the first one to realize that the stars are very, very far away, much further than the planets. And he understood that. You know what parallax is? Parallax is how things seem to shift in their relative positions when you move your head. Okay, so he knew that from the motion of the Earth around the sun, which he had figured out, that if the stars were closer, you would see them apparently move in the sky as the sun went around the Earth. That's called parallax. You know, you're seeing the stars from different positions, and you should see them apparently move unless they're so far away that the angles are too small. So he was the first one to understand that the stars are very, very far away. He was unable to say how far away. There was a whole bunch of stuff which took almost 2,000 years to recover, up to Copernicus and later and others, that Aristarchus had figured out. Copernicus knew about Aristarchus, and he even writes about it in his book. So yeah, he was one of the great geniuses of physics. What happened to him is all of his writings were lost.
In Alexandria, or?
No. I don't think it was Alexandria. I think it was before that. I think the Romans probably destroyed it. But a handful of his disciples, including, I think, what's the one who sat in the bathtub and said Eureka? Archimedes. Archimedes knew about Aristarchus and others, and they mention in their own writings what Aristarchus had discovered. So he was, to me, a great hero.
Okay, well, thanks for that. That was really interesting. Yeah.
Yeah.
Okay, back to Hawking though. Before I derailed you, so
Right.
You don't think he's not up there with Newton, Aristarchus,
I don't
and
think
Einstein?
So. Well, you know, it's a matter of opinion. I wouldn't say no, and I wouldn't say yes. Was he in the class with Feynman? Yeah, I think he was in the class with Feynman. But then there are numerous people throughout the 20th century who were Dirac. In the first half of the 20th century, I personally think Juan Maldasener is in that class. And,
well, the paper on the ADS CFT correspondence has certainly had its impact.
Yeah, Hooft was a great physicist in the same class for sure. So I don't think we would see Hawking as an absolute singularity in the sense that Einstein was, but certainly one of the great physicists of the 20th century, and deservedly so.
And we've talked a bit, or we've mentioned many times, Hawking radiation.
Yeah.
And since that's also integral to the story,
Yeah.
I know that you probably can't get really in depth to what's actually happening quantum mechanically.
You don't need to.
Oh, you don't need to?
You don't need to. You just have to know that if a thing has energy, now remember that energy and mass are the same thing, E equals mc squared. Energy and mass are really just the same thing. Black holes certainly have mass. Big ones have big mass, small ones have smaller mass. So black holes have energy. Bekenstein taught us that they have entropy, and anything that has both entropy and energy has temperature. That's all you really have to know. Anything that has temperature radiates. That's the black body law. Anything with temperature will radiate. Automatically. You don't need to calculate it. So once it has temperature, it radiates. Now, Hawking didn't believe this story. So he did a different calculation which focused directly on the temperature of the black hole or the radiation from the black hole. He did a calculation in quantum field theory which, had he believed Bekenstein, wouldn't have been necessary. He did a calculation using quantum field theory to show that the quantum fields outside a black hole would be excited, would carry some extra energy, and they would carry a flow of particles out away from the black hole. That was an alternate calculation to deriving the temperature of the black hole. But a much more general view of it is that if it has entropy and it has energy, it has temperature. If it has temperature, it radiates.
And just how cold are black holes?
Very cold. Very
how long
cold.
will it take for one to evaporate? Is that anything that could possibly be measured?
Okay, I can't remember exactly. I know I've done this calculation over many, many times, just every time somebody asks me that question. But roughly, I think it was something like 10 to the 70 years. Or
Okay,
it was
so
10 to the 75 years.
very long
vastly
time.
longer, much longer than the age of the universe.
Yeah.
Much longer. Age of the universe today is about 10 to the 10th years. 10 to the 13.8, sorry. Yeah, no, not 13.8 billion years. Okay, we're talking about things like 10 to the 70th years. Much, much longer. So that translates into saying that the black hole is very, very cold.
Is the rough future of the universe going to look like a bunch of black holes accreting, sucking up most of the matter in the universe, and then slowly evaporating into this gaseous nothingness?
This, of course, depends on the details of cosmology. Up till very recently, everybody believed there was this thing called dark energy.
They don't anymore.
They do.
Okay.
But there's some tension about it. It's called the Hubble tension. Mostly, I suspect you should ignore it because I think it will go away. We could talk about why physics is always having these crises like this, where things don't quite seem to fit together. Let's take it for granted that this crisis called the Hubble tension will eventually go away, that experiments will do better, and things will come into a line. Okay, so if everything lines up the way we always thought it would, not always, for the last 20, 25 years, the universe is accelerating in its expansion, but that indicates that it has a horizon. Now, it's not a horizon like a black hole where we're outside the horizon looking in. It's a horizon surrounding us that we're looking out and seeing the horizon. Incidentally, the horizon on the Earth is something that surrounds us, right? Mm-hmm. If we're out on the sea and we look around us, we see the horizon surrounding us. The horizon of cosmology is like that. If we look out far enough in all directions, there's a horizon out there. The horizon is a point of no return. Anything that flows past it is lost. Okay, so mostly what will happen, we're at the center. By definition, we're not because there's any special place called the center, but because we're very arrogant about it, and we say we're at the center. We look out, there's a horizon out there, and what's going to happen, trillion years or something like that, everything that isn't gravitationally bound to our galaxy, stuff which is flowing out with the Hubble expansion, with the Hubble flow, all of that will pass to the horizon, become invisible, disappear, and the only thing that will be left will be our galaxy, which is held together by gravity. It's not participating in this expansion, and maybe the neighboring galaxy, which might fall into our galaxy and become part of it, the Andromeda. All the other galaxies will simply disappear, move out, flow out with the Hubble flow, and just disappear. So the universe will become very, very empty except for ourselves. Because everybody on these other galaxies who's moving out, they say exactly the same thing. They think our galaxy is falling through their horizon. It's much like two ships on the sea. They're moving apart from each other. Each one looks at the other and says, "Oh, that poor fellow went over the horizon."
That's funny.
He says, "He went over the horizon." Well, she says, "He went over the horizon." He says, "She went over the horizon." Neither one felt anything very special, but both of them are right. Each one went over the other one's horizon. That's what's going to happen. Everything will just flow out over the horizon, and we will truly be alone. Not our star will be alone, but our galaxy will be alone. Scary.
Yeah, scary. It's a lot. But getting back to now, I think we've got all of these big pieces of the puzzle on the table, and we're ready to get toward the solution of the black hole war. But just to summarize it, what is the black hole information paradox then? Just what's the standard way of putting it?
Quantum mechanics says information can never be lost. A naive view of black holes says that things fall into the black hole, can't get out, the black hole evaporates, so information is lost. That's the puzzle. It's a conflict of principle.
And along the way to the solution that you eventually came up with, were there any that you tried out that just didn't end up working?
No.
No? You're just kind of guided there?
So what I would say is I was puzzled for a long, long time. When Stephen presented his idea to Hooft and myself in the mansion in San Francisco, I think it was 1981, but I don't remember for sure. I think it was 1981. Both Hooft and I were greatly perturbed and sure he was wrong, but we couldn't figure out why he was wrong. Both of us were very puzzled, very confused, sure Stephen was wrong, but could not figure out why. So we were standing at the blackboard. Stephen was grinning happily over our confusion. I remember Hooft was sweating and looked angry. It wasn't angry at anybody, but he was very, very puzzled, and so was I. So did I try anything that didn't work? No. But I didn't try anything for a long time. I was just confused.
Well, now is, I think, the right time for Hooft to enter the story.
Yeah.
And you just said he was standing there. He looked kind of angry.
No, he wasn't angry.
Whenever I see
a frown on his face, but it was a frown of concentration, not a frown of anger.
But whenever I see photos of him, he's always very well dressed, in a suit. I've communicated with him over email. He's very serious. What's he like as a character and as a physicist?
The first thing about him, that if you get to know him, is he's a man of enormous curiosity. He's curious about everything, how everything works, how seashells form, and you can have the most delightful conversations with him about almost anything. It's not that he's a know-it-all. He's just thought about so many things. My wife and I used to love to have lunch with him when we visit Utrecht in the Netherlands, just because she and he would talk about piano playing. He was a very good pianist, and she played the piano. He and I would talk about physics, but sometimes we would talk about seashells, and sometimes we would talk about the human condition. Yeah, but he's also a contrarian. He tends to not listen to what other people say. And have his own very strong opinions, and sometimes they strongly go against the grain. For example, his views on quantum mechanics today are very different than most physicists. He believes that in the end, quantum mechanics will be completely deterministic. And he's worked very, very hard. Look, he's not a fool. So he knows that how quantum mechanics works better than almost anybody. but he's absolutely convinced that at the rock bottom level or on the cosmic level or the biggest and smallest levels when combined, that quantum mechanics will be completely deterministic. No probabilities, perfectly, completely deterministic. Not many physicists believe that, but some very prominent ones did.
I'd love to talk more about I think it's worth a digression because this is very interesting. I know that, for instance, Bohmian mechanics is deterministic,
but
but
he's
then
definitely not a Bohmian mechanic. That's a naive, very, very naive attempt to make quantum mechanics. Tuft's are much more subtle, but so subtle that nobody else can understand it.
well, yeah, but that's what I was going to say. I mean, other theories or interpretations like spontaneous collapse theories are not deterministic, but then the Schrodinger equation evolves deterministically. So I'm just wondering where it is that his intuition about determinism falls and why he thinks it's at the core of quantum mechanics.
Well, in many examples where you prove that it's not deterministic, you say things like, I could measure the x component of the spin or the y component of the spin. I will randomly decide to choose the y component and measure it. Okay? And I'll get a random answer. A Tuft's view, I think, is there's nothing random about your choice about which it was determined completely from the beginning of the universe what direction you, 13.8 billion years ago, later, would choose to make that measurement in. And so the whole hypothesis that you could randomly or just as a matter of free will choose, for example, whether you choose to measure the position of a particle or the velocity. There's an uncertainty principle that says you can't know both the position and the velocity at the same time. What content is there in that if you have to make a choice? Am I going to measure and I might have many particles, choose to measure this one position, choose to measure that one velocity and collect statistics. But I think a Tuft would say the choice of what you decide to measure is itself deterministic and part of the whole deterministic story. And if you take that into account, that everything, including the decision of what experiments to do, which you think you have free will about whether you measure position or velocity, if you assume that there's no free will about that, that's all deterministic, then I think he would say, well, I know he would say, that the whole world becomes deterministic. Now, that's a little bit crazy. Most physicists don't believe it. It's called superdeterminism or something. I don't think most physicists think that. On the other hand, unlike other people who have these hidden variable views, I think he would say that short of some incredibly complicated experiments that involves every particle in the universe simultaneously, the rules of quantum mechanics as formulated by Dirac or whoever are absolutely correct for any possible experiment that could possibly be done. So he doesn't think that quantum mechanics is wrong in its predictive. He just thinks there's some deeper understanding of it where it'll all become deterministic. Do I agree with him? He's awfully damn smart. He's proved to be right many times. Do I think he's right there? Probably not, but I wouldn't dismiss him.
Given that he has all of these varied interests, I'm curious about how you perceive his attitude toward physics. It seems to me that he's not somebody who just thinks this is a fun game or pastime. He is very determined to get to the bottom of things and understand how the world works. He takes that very seriously.
Absolutely. He certainly does. That's part of his curiosity. His curiosity is so strong, it's not a game. It's an integral part of his personality. It's an integral part of his psychological makeup. And that kind of curiosity can only be sated, can only be finished by knowing the answer. So yeah, he is very serious in that respect. He's
Parenthetic-
also got a good sense of humor, incidentally, but
parenthetically, is this also how you view physics?
yes, very much so.
Okay.
Very much so. Yes, I've always felt he's younger than me by about 7 years, but I've always seen him as I would say a role model in a certain sense. Maybe he sees me as a role model. I don't know, but
Well, now,
I remember telling him once. It was at a birthday party of his in Holland. I got up to give a birthday speech for him, and I said, Gerard, that's his first name, Gerard, I completely agree with you. And he said, yes, but I completely disagree with you.
that's very funny. Returning to the story, though, now that we've got our cast, we've got Gerard at Hooft on the stage. At Hooft. What is the holographic principle, and how did the two of you end up coming up with this idea?
I'm not sure exactly what motivated him. It was certainly the observation that the entropy of a black hole, the information in a black hole, is stored on its surface. For me, trying very hard to understand this, what should we call it, this conflict of views, whether there is something on the inside of the black hole or whether it's all on the horizon and so forth. At some point, just more or less accidentally, I remember the time exactly, I was at Stanford and I was passing in the hallway at an exhibit. There was an exhibit at the Stanford Physics Department, and it was an exhibit of a hologram. And I looked at the hologram. It was a hologram of a very lovely young woman, and she was smiling and moving. She wasn't moving. If you moved, you would be able to see her from 3 dimensions. And I looked at it and I said, you know what? This is very interesting. The real information in that hologram is stored on the photographic, the photographic sheet of photographic material that was surrounding the empty volume. But she appeared to be a 3-dimensional figure inside this. And I said, you know what? There's an example where 2-dimensional information on a surface is completely equivalent in some sense to the information of the 3-dimensional object, which, and that resonated with me. And I said, it is possible mathematically to encode information about 3-dimensional systems on 2-dimensional surfaces. That struck me at the time as possibly an explanation of how all the information on the one hand could be on the horizon of the black hole and still make sense inside the black hole as full 3-dimensional. It struck me that it was very similar in that respect to the way a hologram is both 2-dimensional as a film, as a piece of film, and yet it was encoding a full 3-dimensional reality in a sense. That was probably a silly reason but when I saw that, I said, okay, it must be that there's a mathematical equivalence between what's on the boundary of a system. It doesn't even have to be a black hole, on the boundary of a region of space and things which take place inside it. That was my coming to it through the idea of a hologram and through recognition that we had to somehow put together the idea that all the information is on the surface of the black hole, on the horizon, and yet it's encoding full 3-dimensional stuff inside. I don't know exactly what the Tuft's original motivation was. I'm not sure. I think it was something similar. But we did have a chance to discuss it. I think it was in 1994, and he wasn't very open about it. I don't really know why. I think maybe he wasn't sure it was right or what. But I was visiting at Hooft with my wife, and again, we were sitting in a cafe someplace. It was summer. It was a lovely day. He was talking with her about piano playing, and then we started to talk about physics, and we both started to talk about holograms. He told me at that point that he had written a paper on it. I didn't know about the paper, and I looked it up and I couldn't find it. I had already composed my own paper but hadn't published it. So
Is this the world as a hologram?
yeah. So I put a reference into him and referenced the wrong paper. I couldn't find it. I didn't cut him out. I mean, I referenced the wrong paper. And at that point, I knew that he understood it because we had spoken about it, but I was pretty sure that he hadn't published the idea. Later on, I found out that he published it under a name, I don't mean a tuff, I mean under a title, which conveyed a completely wrong impression about what it was about.
Yeah, it's like higher dimensional reduction of something like that.
Dimensional reduction, which has a completely different meaning in physics. Dimensional reduction, something or other. Didn't have hologram in it, but yeah, it was there. So that was quite exciting when that summer. I remember we spent it in Utrecht, and spent a lot of time exchanging ideas.
So the holographic principle then is just that if you have an n-dimensional volume, all of that information can be encoded in an n-1 dimensional boundary. Okay.
Very much analogous, I'm not saying the same, but very much analogous to the way the two-dimensional film encodes the three-dimensional, what we call the bulk.
And what is the status of this principle? Is it something that can be proven, or it's a conjecture, or it's a useful tool? Certainly a useful tool.
There's a pattern in discoveries like this where they start out as wild speculations which nobody believes. Then they turn into principles, deep principles of physics or of science, and then they become tools, useful tools in studying other things. Originally, the holographic principle was a wild conjecture, was seen as a wild conjecture, and most of my friends and colleagues, their attitude was, oh, Susskind and Hooft used to be good physicists, but they both lost their marbles. And I was told that more than once. I think somebody actually said, lost your marbles. One of the few people who actually believed it completely was Ed Witten.
Really? Yeah. Okay, yeah. I know he has this really famous paper, Anti-de Sitter Space and Holography.
Yeah, that was later though, of course.
Okay.
But, and he and I wrote a paper on anti-de Sitter space and holography, which I think is a better paper, much better paper. Anyway, yeah, Ed was a big, very early proponent of the idea. He was very excited by it, and that was encouraging. But then when Maldacena wrote his paper, it was clear that it was right. It was, there was not possible, even though it may be totally counterintuitive, he had a very concrete example, which was you could do calculations, you could really test out the idea. So it became a principle of physics at that point. But then it also became a tool for studying quantum field theories by using the bulk, by using the duality between the two pictures, where you use simple ideas of what's going on in the bulk, that's the three-dimensional reality, to inform you about how the quantum field theory on the boundary works. So it became a tool. And it's certainly at the center. It's probably the most important development in the quantum theory of gravity since Hawking's discovery of Hawking radiation. It's the center of the whole story. That and entanglement.
Before we get to the world of holography and ADS CFT, how did the holographic principle become this huge, this weapon that kind of won the war, the black hole war? How did it connect to the black holes? And then,
because this anti-de Sitter space, which is surrounded by a boundary, can have black holes in it. These black holes can evaporate. They can be created in the anti-de Sitter space. They can evaporate. But by simply knowing that the description of all of this could be encoded in a quantum theory on the boundary, you are 100% assured that no information can be lost. Because the other description, or two descriptions, one was the black hole in the interior of the anti-de Sitter space. It would be like having a black hole at the center of your hologram. Okay? But you know that the hologram is actually described mathematically precisely by the boundary, by the film at the boundary, the details of it, and you know that that description is quantum mechanics, quantum field theory to be precise. And quantum field theory cannot lose information. So that was the thing that broke the back of the information loss hypothesis.
Interesting. I had thought that it kind of seemed like the war was won before ADS-CFT because there were ways of making use of the holographic principle with string theory on the boundary of the black hole.
Yeah, right. There were ways of thinking about the black holes that way. The first one was a way that I put forward, which was actually just ordinary string theory on the boundary of the black hole. That was successful in explaining the entropy to within a factor of 4. It wasn't able to get the detail quite right. And then there was this wonderful paper of Strominger and
Kummer and
Vafa that found an example where they could be totally precise about the relation between black hole entropy and area. So yes, that was a predecessor of it. When was that? That was 1996, I think. I forgot. And then there was the paper by myself and a couple of other people on what's called matrix theory, which was kind of a forerunner of ADS-CFT, a similar kind of thing. Again, a holographic kind of description of something. But the ADS-CFT was a lot clearer, it wasn't more precise. It had the same degree of precision, but it was much easier to understand, and so it captured people's attention, and properly so. It captured their attention more than the so-called matrix theory that who was it? Myself, Steve Schenker, Willie Fischler, and Tom Banks. It's called BFSS. Now people have gotten more interested in the BFSS idea, and it's being carried out more consistently. But both as a matter of physics and as a matter of what shall we call it, cultural development, the ADS-CFT was the thing that really nailed it to the point where Stephen himself had to give up.
Really? It was ADS-CFT that did it for him?
I think so.
One reason that surprises me is just I've never heard of Stephen described as a string theorist, and that's obviously integral to ADS-CFT, so it surprises me that he would take it so seriously.
Well, look, he wasn't a string theorist, but he was very, very smart. He knew when he had lost. Because he tried to sort of turn it about and make it sound more like what he had said, but he knew. And it took him a few years after the ADS-CFT, but look, we were friends. I do remember that he and I and Ann, my wife, had dinner with him at his house with his daughter, and he had basically given up. What I have to say about him, he was delighted by the whole story.
By the book?
No. He was delighted by the ADS story. He knew he had lost, and he wasn't unhappy about it.
That's great.
Yeah, he was marvelous. It was something special.
I think that well, there are a number of reasons for this. ADS CFT is vital to winning the war. Yeah. It's, the huge outgrowth of the holographic principle that you and Hooft developed, and it's just the most cited paper, I think, of all time now in high energy particle physics. So. I think it might be worth talking a little bit more about it. You used some words like duality. Yeah. I'm not sure people know what that means.
It just means equivalence between two descriptions of the same thing.
So what is the duality at the heart of ADS CFT?
First, take the case of the hologram. There's a description of the hologram in terms of what's going on the film. And if you were to look through a microscope at the film surrounding the hologram, what you would see is all of a bunch of little tiny scratches and random looking, nothing that looks anything like the thing that it's supposed to be encoding. What does it look like? It just looks like a bunch of random scratches, which are not truly random, little marks on the film. On the other hand, it has exactly the same information as the three-dimensional thing that it was created from. This pretty girl, in the case of the hologram that I was watching, it has exactly the same information, at least of her surface, if not her interior. So that's a duality. Duality between two descriptions. One description says ears, nose, hair, eyeballs, and a certain shape, and the other description says tiny, tiny scratches on a piece of photographic film. If you knew how to analyze those scratches the right way, how to do the right kinds of Fourier transforms and so forth, in principle, you could take those tiny scratches and reconstruct what they were pictures of, what they were holograms of, the full three-dimensional and everything else. But it would be very hard. It would be very, very hard and complex to do that reconstruction. So we call those dual descriptions, D-U-A-L, not D-O-O-L, dual descriptions of the same thing. One, in terms of properties of the film, the other in terms of the obvious properties of the object which it's there to encode. The same thing is true in the ADS-CFT idea. Whatever ADS is, it's a space with a boundary. It's a space that has a boundary surrounding it, and the duality is a duality between a theory that lives on this boundary. It's a quantum field theory that lives on the boundary, just like the information on the hologram lives on the surface, on the film, and what takes place in the bulk or the interior of the anti-de Sitter space, which is more like what's taking place inside the hologram, in the three-dimensional reality of the hologram. So the duality is two different descriptions of the same thing, one in terms of what's going on in the interior. For that, you use gravity, you use general relativity, you use black hole physics in the three-dimensional reality inside. And the other description is in terms of this very random kind of quantum field theory description involving lots of fluctuation and lots of stuff that you would not easily recognize what it's encoding, but which does encode exactly the same thing. But that's what duality means. It means two different descriptions which seem very different from each other, but in what is in principle the same thing.
Okay, just to summarize it, and then I think we'll pretty much be done with the black hole war.
Well,
So the idea, this,
you're going to be done with me soon.
yeah, so the ADS CFT correspondence, on the one hand, you have, I think it's type 2B string theory describing the bulk, and then you've got a conformal field theory on the boundary of the anti-de Sitter space. In this string-theoretic description,
Okay, that's just highly formalized language for what I said.
yes,
Yeah.
but I just want to make sure that I have it clear. In the bulk, you have these black holes, they accrete and they evaporate, and because it is all captured by this equivalence on the boundary and no information is lost because it's quantum field theoretical,
Right.
that's how you win the black hole
That's
war.
how the black hole war was ultimately won. I
Okay,
would say.
perfect. And then the final question on that is this pretty much settled in the physics community now?
Yeah, I think so. Look, I tend to interact with a group of people who share my own views. Half of them are my students, incidentally. I tend to interact with them. How many people are there out there? I think some of the older relativists may still be skeptical. People like Bill Unruh, but I may be wrong about that now. I haven't seen Bill for many, many years. Bill Unruh was one of the pioneers in Hawking radiation physics. He was very, very skeptical about all of this. Another was Bob Wald, who was one of the true great relativists of the late 20th century. He was very skeptical whether they've come around. But remember that this was an older generation who were brought up on the rules of general relativity, classical general relativity, and this was all very, very new to them. Okay, it was also new to the young people who invented it, like me, who was, I don't know, I'm not sure how old I was. I was in my mid-50s, I think, with the holographic principle. And I'm probably older than both of them, both Unruh, but nevertheless, I'm young at heart. So I consider myself one of the young people. The young people, it was new to them too, but young people don't have all the baggage of long life having believed one thing and then suddenly being told to believe something else. So the older generation of relativists, I think, were skeptical and may still be skeptical. People like Wald and Unruh, I don't know. But barring them, I think it's completely settled.
Earlier in our conversation, you said that periodically there are these crises in physics, and the black hole war is one of them.
No, I wasn't thinking about the black hole. I was thinking about these crises where experiments don't seem to agree, or where experiment seems to disagree with theory. An example being the gyromagnetic ratio of the muon, which if you use the same physics as for the electron, you get a certain number from ordinary quantum field theory, quantum electrodynamics in that case. But if you measure it, somewheres in the 12th decimal place or something, the experiment and the calculation disagreed. This is one example of the kind of crisis I was talking about. Crises which usually have to do with discrepancies between theory and experiment. Why do they happen? Why are they always there? And the reason is because both theory and experiment are always working on the edge of the technology. Experiment, for obvious reasons, they're very hard. You don't do an experiment now in 3 weeks. It's the better part of a scientific lifetime to do an experiment. It can take 20, 30 years to do an experiment. They're very, very hard. And you're always working at the very, very edge of the technology. You're working at the edge of the statistical fluctuations and things. And at the same time, if the experiments previous to that had pushed the theory so hard that you might be working in the 12th decimal place of the theory. So it's not, to my mind, at all surprising that a period takes place where there's discrepancy and everybody gets very exercised about it and very worried about it. and then it goes away. And then it goes away. Okay, so we're facing now a couple of these kind of crises in cosmology.
Right now.
Yeah, there's one that's called the Hubble tension. The Hubble tension, you know what the Hubble constant is? It's the rate of expansion of the universe today. There are two ways of determining it. One is by direct observation of objects moving away from us, measuring their velocity and their distance. That's, of course, not so simple. You use supernova and all kinds of things, but it's sort of direct measurement of the expansion of the universe today, or at least seen from through ordinary telescopes, or maybe fancy telescopes. Okay, that was one calculation. It leads to a certain number. I think it's 74 something per something per something. Kilometers per second per megaparsec. But okay, so that was one measurement of the Hubble expansion. There was another method which you go way back to the era when the cosmic microwave radiation was being formed in the very hot plasma. You can see that at a great distance away from us. You want to go way back in time. The way you go way back in time is going to very large distances. You measure the properties of the cosmic microwave background. You use it to inform you about what was going on at that time. And then you use the equations of cosmology to run it from the very remote past up till today. The Freeman-Robertson-Walker equations, some knowledge about equations of state, this, that, and other things, stuff having to do with something called baryonic acoustic oscillations. Doesn't matter what it is. It's using a theory about what happened 13.8 billion light years, 13.8 billion years ago, and then using equations to extrapolate it to today. It disagrees with that 74. It gives you 68 or something. Well, what's the difference between 68 and 74? No big deal. Unless you happen to be either the group who did one experiment or the other and who are absolutely convinced that they are correct. Okay? And that's what's happening now. Both experiments are kind of at the edge of technology. Nevertheless, the proponents of these two numbers, who are, wonderful physicists, these are not amateurs. These are not. These are super good scientists. One group is absolutely certain their number is correct, and the other group is absolutely certain their number is correct. One resolution might be that something unknown or unaccounted for happened in between during this time from the microwave radiation to today. It's possible, but that's a crisis now. Will that crisis go away? Will some new physics come in between? We don't know. I always guess, doesn't matter what it is, when a crisis like this happens, I always guess it's going to go away. And I've almost always been right.
Why do you say almost? What's the exception?
I'm trying to remember. Very early on, I do remember. Very early on, Jim Peebles was claiming that there was some evidence for something like dark energy, for something like a cosmological constant, or a little bit different perhaps. This was long ago, and he was quoting data. I thought that seemed very unlikely to me that there was a cosmological constant. That seemed, and I was pretty sure that his data was probably, his data was right. There was a cosmological constant. I was wrong about that one.
Okay, that's funny.
Yeah.
Well,
as far as I can remember, I think it's the only one I was wrong about. Not because I'm such a genius, but because I always say it's going to go away.
The last thing I want to ask you today brings the black hole war, some of the things we've been talking about, into the present. I just interviewed your colleague Raphael Busso, who I know is one of your students. And
He was not one of my students, one of my postdocs here.
yeah.
He was a student of Stephen Hawking's.
Okay. Interesting. I assume that if somebody's your postdoc, they're your student, but
Well,
I
in
guess
some
not.
sense, I
In
suppose.
some sense. Okay.
But the young people I've worked with, I've learned as much from them as they did from me.
But he's very much working on holography. And I know that many physicists are. It is extremely vital and robust today.
Yes, that's
And what I wanted to ask you about is what the state is both of holography and M theory today as you see them.
Well, what is M theory? M theory is a particular example of one of the many possible things that string theory can do. M theory is some limit of some particular string theory in which it goes and becomes an 11-dimensional gravitational theory. It's not thought to be the theory of the world.
It's not anymore? I mean,
I
thought
think
it
once
was. Oh, really?
The world is not 11-dimensional. I'm not sure where this idea that M theory was there's just a whole bunch of different corners of the parameter space which describe different kinds of, let's call them universes, and they have different dimensionality, they have different properties. And M theory, I think, was originally intended to be some corner where the physics was flat, 11-dimensional physics. Why that was seen as somehow a better theory of everything than any of the other corners, it was not a good theory of the real world. The real world is just not 11-dimensional. One thing that did happen with what is called M theory is it was the first example in which there was a complete quantum description, holographic quantum description of that particular theory, of that particular, that was this BFSS matrix model, but there was nothing particularly, what shall I say, nothing. It was not a theory of the real world. Neither was anti-de Sitter space. Right. It was just one corner of the parameter space.
Yeah, my impression was that it was believed that all of the different string theories, type 1, 2A, 2B, these were all limits of M theory, and M theory was
also a limit of them. They could all be represented as what we would call compactifications of this 11-dimensional theory. And that's true, but the 11-dimensional theory itself can just be thought of as a limit of any one of these in some unusual range of parameters. So I don't see anything more fundamental about it than any of the others.
Then maybe the question that I should ask is, in addition to continued work on holography, ADS-CFT, and its offshoots, are high-energy particle physicists and string theorists still working on string theory or its offshoots as a final theory of the world?
Okay, I have a view of that, which my colleagues, you may have seen it on other interviews. I will say what it is here. I have a view of it which is probably a little different than most of my colleagues, although by now they might have the same view. My view of it goes something like this. So there's this very precise mathematical structure. It includes M theory, it includes type 2B, type 2A, and so forth, and they're all exactly supersymmetric, and the supersymmetry is absolutely essential to their stability, to their rigor, to their mathematical existence, let's call it. There is absolutely no doubt whatever that that is not the theory of the real world. The real world is just not supersymmetric. Some of these people say, oh, okay, but we'll spontaneously break supersymmetry. Nobody has ever been able to do that. That has never been able to be. So the real string theory that people know and understand, and that the mathematicians consider, and not just the mathematicians, the mathematical physicists like myself, consider precise. That is not the theory of the real world. It is definitely not. The real world is not supersymmetric. Okay, so what do people mean when they say string theory? And let's call it string theory with a small s now. They mean something that's inspired by the precise theory, something which goes beyond it, something with bigger boundaries, and we just don't know what that thing is. We simply do not know what generalization of supersymmetric string theories are possible. We do not know. Nobody knows. Nevertheless, that's the idea, that there's some expansion of the boundaries of what string theory is beyond this capital S theory to what I call small s string theory, or string-inspired theory, or that nobody has ever defined. Incidentally, I'm a believer in this, and that the real world is outside the edges of what we call capital S string theory, but in some range of theories which is inspired, maybe even has strings, but all kinds of theories have strings in them, incidentally. Superconductors have strings in them. My shoelaces have strings in them. All kinds of things have strings in them. And not all string theories have strings. So whether a theory has strings in it or not is not the criteria for whether it's string theory. Spaghetti has strings. Okay, so my view of it is we don't know how the real world is connected to this very precise string theory. So what is the value of the precise theory? Well, first of all, perhaps it will inspire a generalization. It may. But if nothing else, it has taught us with certainty that quantum mechanics and gravity can coexist. That all of these paradoxes, like Stephen's paradox and the paradox of infinities and all that stuff, that tell you that quantum mechanics and gravity cannot coexist, they were all wrong. That we know with certainty now, because of capital S string theory, that quantum mechanics and gravity do coexist and can coexist. That's been the main output from it. And the attempts at turning it into, or let's put this, let's say deriving the standard model of particles from it, that's been largely failure. Not total failure. It is true that some of these theories look a good deal like the standard model, but they're not. They're not. So that doesn't mean that we should get rid of string theory as a theory of the world. It means we should just be honest with ourselves and not be content with something that doesn't work, and not tell the media. Incidentally, most of my friends who are string theorists don't go around proselytizing for it in the media and so forth. They don't. But somehow, and because of this, unfortunately, in some broader segment of the public, and that includes physicists, it's been interpreted that string theory is a failure. That's not correct. String theory is a structure, a mathematical structure, which has taught us all kinds of things about gravity and quantum mechanics and how they can coexist. But it has not been able to confront the real non-supersymmetric world yet, and maybe never. Could it be that it's totally wrong and it's completely wrong-headed and the real theory of the real world has nothing whatever to do with string theory? Yes, it could be. I rather doubt it. I don't think so. I think it gets close enough that we should continue to look for how it can be expanded. But I'm 84 years old. I also have the baggage of my first contact with string theory was 1969, and as one of the so-called fathers of the subject, I have a proprietary interest in it. So you shouldn't take from me if I say that I think maybe it can work in some expanded form. But I also think the skeptics are way off base in what they say.
So you say this capital S string theory is not the right theory, but lowercase s string theory, something string theory inspired, is what you believe to be on track. Now, this theory may or may not have strings, but one thing that
I think it does have strings. But
you think it does have strings?
Yeah, I do. But incidentally, M theory, as this 11-dimensional theory, does not have any
brains,
strings.
Right?
Has brains.
The question that I have, though, is you said that our world is not 11-dimensional, and that's one reason why M theory isn't the right theory.
But I don't worry about that as much as I worry about the need for supersymmetry.
But when you say it's string theory inspired, one of the biggest things that people know about string theory is that there are these compactified small dimensions around which strings.
That's fine.
Why? So you think that there still might be these extra curled up dimensions?
Maybe, yeah.
Okay, then what is it about 11 that is special versus 10?
Oh boy. No, it's nothing that's particularly special about 11 versus 10. Or a more important question is what's special about 10 and 11, but especially what's special about 11. It's a highly technical thing. 11 dimensions is simply the largest dimension in which you can formulate relativistically covariant supersymmetric theories. It's just, you cannot push it past 11. That does not sound like a terribly good reason for, but nevertheless, it is the limiting number of dimensions, the biggest number of dimensions in which these theories can be formulated. Technical reasons, they're very technical, and I'm not even sure I could tell you what they are. It's the largest number of dimensions in which a theory can be supersymmetric, a relativistic theory. A bunch of little bits of algebra you put together, and out comes the number 11. So from a technical, mathematical, supersymmetric point of view, it seems to be special.
And in this same vein, I mentioned Raphael Busso earlier, and I believe this was a conversation that I had with Raphael, but it wasn't on camera, where we were talking about supersymmetry and the fact that super partners haven't been found at CERN in the Large Hadron Collider.
Right.
And I believe...
But even if they had been found, the world is not supersymmetric. It's not supersymmetric because the super partners don't have the same mass as their other half. And that's enough to ruin capital S string theory, even had they been found.
Really? So that suggests to me then that you've been pretty confident that the world is not supersymmetric for a very long time.
Oh, yeah. Yeah. However, I would have said, had super partners been discovered, I would have said that's very good for the idea of small s string theory.
I see. Okay. Very interesting. And then the last thing, going back to ADS-CFT again, ADS-CFT is built on type 2b supersymmetric string theory.
One version of it, yes.
One version of it.
I always forget what's type 2 and type 3, type 4, type 7. No, I know what they are, but I have to remind myself. And the B and the A.
But this is a supersymmetric theory, and the world is not supersymmetrical. You also said that the world is not ADS space.
Both of those things are true.
Mm-hmm.
The world is definitely not anti-de Sitter space. And the precise versions, the stable versions, the versions that actually make sense of the ADS-CFT are all supersymmetric.
Is there work going into creating a version of ADS-CFT that might better match our space and be perhaps a more concrete
No, I
way
don't
of
think there's any way that our space-time can be anti-de Sitter space.
Oh, I'm saying like a DS-CFT
Oh.
or something like that that might
Okay,
actually be
good.
our world.
Yes. Is there work going on? That's been my focus for the last 5 years, for sure.
DS-CFT?
Not DS-CFT. That's a particular version of but holographic description of the horizon of de Sitter space. Very much so. That's very much. And one particular example of it, doesn't matter what it is, it's a mathematical example of it, but yes, there is some motion in that direction now. And it's going to get bigger.
What do you mean it's going to get bigger?
No, I mean, what I mean by getting bigger, I don't mean that the space is going to get bigger.
But
I mean that the number of people, the activity in it will get bigger, and it will get very big.
Working on a holographic theory that could describe our world?
Well, no, I think that's still premature. I don't think we're near that. Working on a holographic theory that can describe de Sitter space. Our world is not really de Sitter space. It's tending toward de Sitter space with time. The degree to which it is really eternal de Sitter space, that's not completely known, but probably not. The world seems to be evolving towards something that looks very much like de Sitter space. Whether it be eternally stable after that, we don't know. But one can try to describe a mathematically precise, eternal, exact form of de Sitter space, which again wouldn't be our world exactly, but it would be a lot closer. So you can forget all of that. Yes, our world is more like de Sitter space, much more like de Sitter space. And it has scared people. I mean, I don't mean it scared them that we live in de Sitter space.
Yeah.
I mean that the lack of a boundary, the lack of supersymmetry, the lack of all the things that made it possible to be very precise about anti-de Sitter space has scared people away from thinking about de Sitter space. I talk to young people all the time, and I say, why aren't you thinking about de Sitter space? Oh, I won't be able to get a job. That's not a good reason.
I thought that de Sitter space had a boundary. It was just time-like rather than...
No, I mean a spatial boundary, a boundary of the same kind. The boundary of anti-de Sitter space would be said to be time-like. It contains one direction, which is time. The corresponding boundary of de Sitter space is space-like. Different kind of animal, not amenable to a holographic description. Not the right thing for a holographic description. So people invented something called DS-CFT, which I'm not a fan of. I don't think it's the right idea. But whatever the right idea is, there are very few people working toward this now. I would hope that there's going to be an explosion of activity in it.
Last question. You said that our world is tending toward DS-CFT.
With time, it's getting more and more. That was what I told you before, that all the galaxies are going to go out past the horizon. Our space is going to become empty de Sitter space, except for our own galaxy, which we happen to be sitting on.
But does that mean then that you don't think that our world is one that has a space-like boundary?
I do. Yeah, that's what I think. Well, okay, it's a different kind of boundary. It's a horizon instead of a cold boundary of the kind that anti-de Sitter space has. Our world, meaning the world that we can see by any kind of experiment, is bounded by a horizon. That horizon is a kind of boundary of our world. But it's not the same kind of boundary as anti-de Sitter space. So it requires some new ideas, and it requires. Tell you the truth, I don't know why more people aren't working on it. They should be. I talk to a lot of young people, as I said, and I ask them, and they're just afraid of it. They're afraid of it because the ideas aren't there. They don't know how to think about it, and they're afraid they won't be able to get a job if they. Not that there's a prejudice against it. There's no prejudice against it, but they just won't be able to write papers.
Yeah. Well, this has been a marathon session.
Yeah,
Thank you so much. This has been so absolutely excellent. I love the Black Hole War. I hope our listeners check it out.
Yeah, okay. Thank you.